Hello, everyone, and thank you for joining us for this session. If you have not done so already, please take a moment to respond to the poll on your screen. How many individuals are attending this webinar at your location? If there are more than 5, please enter the number of attendees present in the questions box. We will begin shortly. Great, and thank you all for joining us today for EPA's 17th Annual Drinking Water Workshop. We are very glad that you could join us today for session 5B on source and treatment, contaminant removal. I will now turn it over to Wendi Wilkes from the Association of State Drinking Water Administrators, who will help moderate the session and introduce our first speaker.
Hi, good afternoon, good morning, hello. Welcome or welcome back to EPA's 17th Annual Drinking Water Workshop. And thank you all for joining us. Also, congratulations on choosing to attend the best session at the workshop. Only joking, but we do have a stellar lineup for you guys today. I want to make sure everyone's in the right place. This session is the source and treatment track, or 5B, on contaminant removal. Before our presentation begins, please take a quick moment to look through the webinar panel on your screen. This is how you're going to be able to communicate with us and ask questions. We encourage you to ask questions for the speakers throughout the webinar, and you can do that by entering them into the question box. We're going to go ahead and hold all questions for the speakers until the end of our Q&A session, but please go ahead and send them throughout. You can also use the question box if you're having any technical difficulties, and the technical support folks will be able to assist you with that. So let's go ahead and jump in here. Our first speaker today is Asher Keithley, an environmental engineer and postdoctoral fellow at EPA's Office of Research and Development, who will be talking about biological treatment and nitrate. Asher is involved in multiple biological treatment projects that are focused on evaluating treatment performance, investigating microbial communities, and optimizing design, and previously worked for an engineering firm in New England on a variety of drinking water treatment and distribution projects. Okay, Asher, I am officially passing the presentation over to you.
Great, and can you see my slides?
Not just yet. I think it might be coming up.
Let me re-share your slides real quick.
Thank you.
Yep. Sorry, one moment. There we go. Perfect, great.
All right, thank you all for being here this afternoon. I'm excited to share with you some information on biological treatment for nitrate removal and some of the exciting research that we're doing here at the EPA in Cincinnati. I would like to start by acknowledging my co-authors, Dan Williams, Nick Dugan, and Darren Lytle. So first, why nitrate? Nitrate is a regulated contaminant with a maximum contaminant level of 10 milligrams per liter as nitrogen. That MCL was set around the health concern for blue baby syndrome, because within the body, nitrate gets converted to nitrite, which can bind to hemoglobin, and then we don't have enough oxygen in the blood. Some recent research has shown that nitrate can also lead to the formation of N-nitroso compounds within the body, and those can increase the risk of colorectal cancer, thyroid disease, and birth defects. So these health concerns could be problematic at, or have a risk at a lower concentration. So looking at nitrate occurrence, this is a map of predicted groundwater concentrations in shallow, recently charged groundwaters. And the nitrate in orange is 5 to 10 milligrams per liter, so getting close to the MCL. And then areas in red have concentrations above 10, so above the MCL. And if we look at where that's occurring within the country, it's in the Central Valley of California, Eastern Washington, all through the Great Plains, some in the Midwest, like Indiana and Illinois, and then along the East Coast, particularly in the Mid-Atlantic. So nitrate's a concern throughout the country. And looking at trends over the last 30 years, nitrate concentrations in groundwater tend to be increasing. The orange arrows on this map indicate an increase over that period of time, and large increases are seen in the Central Valley of California. The concentration has decreased some in eastern Washington, and then the black squares indicate that there hasn't really been a significant change. And increases in nitrate are most commonly observed when we're looking at shallow, unconfined aquifers where the land use is agricultural. And looking now at MCL violations, these figures are from a couple papers by Mike Panino. And first, they looked at MCL violations in groundwater systems versus surface water systems since 1994. And the percentage of groundwater systems in violation has increased over that period of time, whereas surface water systems are decreasing. And they found that people served by small and intermediate-sized groundwater systems may be at a higher risk of prolonged nitrate exposure. And to follow up on that, they looked at the probability that a system in a given location would violate the MCL. So looking at this map on the right, areas in yellow-orange have a probability of greater than 0.5 of violating the MCL. And all these red dots indicate that an MCL violation was observed between 2013 to 2017. And that maps on really according to where nitrate is observed. So that's the setting for this. So if a system has nitrate in their groundwater and they decide to proceed with treatment, what are the treatment options that are available? I'd say most common is probably ion exchange. Some advantages of ion exchange are that it's easy to operate and it's commonly used. But a disadvantage is that it generates a waste brine that must be disposed of. And particularly for inland communities dealing with this high concentrated nitrate and high TDS brine can be a concern and can be expensive. Another option is reverse osmosis, with the advantage that it removes multiple contaminants. But some drawbacks are that it has a higher cost and greater operational complexity. And again, there's this concentrated brine that requires disposal. Both ion exchange and reverse osmosis work by separating nitrate from the main process flow, but nitrate remains present as nitrate. So another option is biological treatment or denitrification, in which bacteria convert the nitrate to nitrogen gas, which is innocuous and gets released to the atmosphere. So there's no concentrated waste stream with denitrification. Another advantage is that it can remove multiple contaminants. You can remove other oxyanions like chromate or perchlorate if you set the operating conditions right. One drawback of biological treatment, at least on the drinking water side, is that there's less operating experience within the U.S. So this is what we're going to focus on for the remainder of my talk. All right, so a little bit about denitrification. This is the reaction pathway that's carried out through a series of enzyme catalyzed reactions within a single bacteria. So one cell will take it from nitrate to nitrite to nitric oxide to nitrous oxide to nitrogen gas. And in this process, nitrate would be the terminal electron acceptor. And you have to get rid of any dissolved oxygen in the water first before they'll use nitrate, because in general, bacteria get more energy from oxygen. So if these groundwaters are under oxidative conditions, so we expect dissolved oxygen to be present, and that gets removed first, and then nitrate starts to be consumed. And then we need an electron donor. So this can run as a heterotrophic process, in which case organic carbon would be the electron donor, or it could be autotrophic with hydrogen gas or sulfur as the donor. In general, heterotrophic denitrification is a faster process, and that's what's commonly been used at full scale. And possible donors would be acetic acid, ethanol, and methanol, with acetic acid sort of being the preferred option. So this is a schematic of, we have the oxygen and nitrate coming into our little microorganism, and the acetic acid as the donor, and then this bacteria or the single cell would be sort of our redox factory, and coming out the other end is water and nitrogen gas. And then they're also going to synthesize more biomass and some soluble microbial products, just byproducts of these reactions. So if we look at what sort of acetic acid feed is required here, and just how much biomass we're producing, let's say we have a water with 8 milligrams per liter of DO and 15 milligrams per liter of nitrate, then in total we would need 74 milligrams per liter of acetic acid, which as DOC would be close to 29 milligrams per liter. So we're talking about a lot of organic donor here. And then, of course, that's going to produce biomass. And the point I want to make here is that the oxygen constitutes 15 to 20% of the total acetic acid requirement, and of the biomass produced. So that's not our contaminant of concern, and yet it's contributing a substantial, and not substantial, but it's not inconsequential. So the oxygen does have this requirement associated with it, or these drawbacks. So looking at what a treatment train might look like, for full-scale experience, there are several facilities operating in Europe and a few in California. And as I mentioned, most of these operate heterotrophically. They're designed to treat a range of flows from like 0.3 up to more than 5 mgd. So the small and intermediate sized systems that we're focused on here fit within this, and then the nitrate and the raw water treating anywhere from 11 up to 20 milligrams per liter. So in this treatment train, we have raw water with DO and nitrate. Then to that, we would add acetic acid and phosphate. I like to think of this as the juice and the vitamins. And that goes into our anoxic bioreactor. And in that, the oxygen gets consumed and the nitrate gets consumed by bacteria, so that coming out, ideally, we have no DO and no nitrate. And then the water would get run through an aerator and through a polishing aerobic biofilter. And then we add chlorine and send it out to distribution. There are a few different designs for this anoxic bioreactor that I want to talk about. The first is a fixed bed. So here we would have influent coming in at the top, packed with granular media like anthracite or sand, and then the effluent comes out the bottom. These systems tend to need to be backwashed every 24 to 48 hours, and more frequently you would bump it to degas about every 12 to 24 hours, because we are producing nitrogen gas, and those form as little bubbles within the packed bed, and those bubbles disrupt the flow path and cause issues hydraulically. So this bump would be at a lower flow rate and for a shorter duration, and happening more frequent than the full backwash. Another possible design is a moving bed bioreactor, in which case the influent comes in at the bottom and is pumped up through a bed, and the effluent comes out the top. And there's a recycle stream from the effluent end back to the influent to get the contact time that we need. And in this, the bed would expand by like 40 to 60%. Again, you could have GAC or sand as the media in there. And this configuration doesn't require any backwashing because it's constantly fluidized. But there is a greater pumping requirement associated with it. So we've been working on an innovative denitrification reactor that's a fixed bed bubble column. So in this, we have water coming in at the top and flowing out the bottom through a packed bed. We've been working with gravel so far that's about a 1/2 inch in diameter. And then counter current to that, we're sparging in nitrogen gas from the bottom. So we're taking advantage of that gas transfer to strip out the dissolved oxygen in the water. So our bacteria only need to remove nitrate. Some potential benefits of this configuration are that you would have less frequent backwashing because there's a larger media size. We're dealing with lower biomass concentrations because they're not growing on oxygen. And in a way, it's sort of a continuous degassing, so we might not accumulate those bubbles within the bed to the same extent. And also, there could be a slightly lower chemical cost associated with the lower acetic acid feed requirements. These are the schematics of the two systems that we've been testing. The first is this bubble column in System A, where we feed in dechlorinated tap water that's amended with acetic acid, nitrate, phosphate, and then bicarbonate for pH control. So that goes through a gravel bed, and then we have a nitrogen generator hooked up to it, continuously supplying nitrogen. That gets pumped through an aeration column where we add compressed air. Then it goes through a dual media polishing filter with anthracite and sand. In System B, it's a very similar influent, starting with dechlorinated tap water, to which we add acetic acid, slightly more, nitrate, phosphate, and then sodium hydroxide as for pH control. And that's a dual media filter of anthracite over sand. And in this presentation, I'm just going to be talking about the two anoxic reactors, the bubble column and the fixed bed. This is a photo of the columns down in the lab. They're 7 feet tall, clear PVC, 3 inches in diameter. We've been running them at a flow rate of 250 mils per minute, giving us an empty bed contact time of 14 minutes. I think we can push that lower. And then in System A, in the bubble column, we're feeding nitrogen at 2 liters per minute. We're targeting an influent nitrate concentration of 15 milligrams per liter. And then adding acetic acid, less in System A than in System B, but we're still dealing with pretty high DOC concentrations here. And then also adding phosphorus. So for the operating timeline, we designed this study to assess the impact of intermittent operation, running 9 hours per day, 5 days per week, which might be similar to the operating schedule at a small groundwater system. So we started that up in December, and through the winter, did some optimization to the influent by adjusting the pH and then increasing the acetic acid feed. And then we've been able to test some different longer intermittent operation scenarios. So the system was shut down for about a month, a few different times since March, and then we've run it for maybe 2 to 3 weeks and then shut it off again for different reasons. And it's been back up and running since August, or early August. And so, you know, some interesting testing scenarios that we get to look at. All right, moving into the data, I want to take a second to orient you to these figures because this is how all the slides will look. On the left, we have System A, the bubble column, and that's in blue. On the right, System B, the fixed bed, is in orange. The top of the bed, or the influent, will be in a darker color, and then the effluent will be in a lighter color. So we're looking here at the dissolved oxygen concentrations, and in the bubble column, we see that the sparging with nitrogen is doing its job. The DO at the top is less than 2, usually less than 1, whereas in the fixed bed, the DO was up at 9 in the winter, and now it's been more around 6.5. And then in both systems, the effluent DO is less than 0.5 milligrams per liter, so these are anoxic reactors. Looking here at the nitrate, we see that both systems can get the nitrate down to less than 1 milligram per liter. So the MCL is shown here in black as a dashed line at 10. Our influence has been between probably 14 and 16 milligrams per liter, so right around that target of 15. And after making some adjustments to the influent feed in the winter, the effluent nitrate has been quite low. So they're taking nitrate from 15 down to less than 1, usually 0.5, and the bacteria are eating a bunch and doing their job. And now looking at nitrite, because nitrite accumulation is a concern in denitrification systems. If there's not enough substrate available, enough organic carbon, or if the pH conditions are wrong, then the bacteria will stop at nitrite and not take it all the way to nitrogen gas. And nitrite, as you know, has an MCL of 1 milligram per liter, so we want to avoid this accumulation. So early on in the operation, we were seeing high nitrite concentrations coming out of both systems, but after increasing the acetic acid, it's been well below 1, usually less than 0.2, so everything's operating well. So as I hinted, pH is an important operating parameter. Denitrifying bacteria prefer pH in the range of 7 to 9, so they're not as picky as nitrifiers, but there is still this preferred range, and if the pH gets above that, then we can see nitrite accumulation. And there are a lot of different processes that are impacting pH. So on the bottom here are a couple of theoretical stoichiometry equations that are rounded, so there's a bit of error in these numbers, but we can see that growing on oxygen consumes H+, and growing on nitrate consumes like 1.95 moles of H+ per mole of nitrate. So we're consuming H+, producing some CO2, adding the acetic acid to the influent consumes alkalinity, and then, at least in the bubble column, sparging with nitrogen will strip out some CO2 as well. So lots of processes impacting pH. So as we look at the pH profiles, since making adjustments to the influent, the pH coming into each system is between 7 and 7.5. And sometimes the pH in the effluent was up around 9, but more recently it's been around 8.5. So we're in a range, and we've been able to control the pH, which is good. Looking at we've looked at ATP as a measure of the biological activity in each of these systems. And to do that, we collected composite samples of the backwash water. And so this table is showing ATP, the average and min and max, measured from each column. And we're definitely seeing higher ATP concentrations in the fixed bed at like 17,200 picograms per mil, as opposed to 11,800. And we would expect this. In System B, the bacteria are growing on both oxygen and nitrate, and so we would expect there to be more ATP. And this is a photo of the fixed bed of the anthracite layer at the top of that column, taken after the system had been online for maybe 2 days and right before backwashing. And you can see all these bubbles in the bed, and really the impact of all the biological activity within this packed bed. which leads us into backwashing and the backwash frequency. So with all this food, we're going to get a lot of growth, and as I mentioned, the bubbles can disrupt the flow path. So looking at the head loss that we've observed in each of these systems, in system B, we can get anywhere from like 20 to 70 inches of head loss over the course of 2 to 3 days of having the system online, or after backwashing. Whereas in the bubble column, we would get maybe 4 inches of head loss in 3 to 4 days. And definitely the size of the media is a factor in this, but also system B does have a greater activity going on in it. This figure is showing the filter runtimes that we've observed, not observed, have implemented. And the blue dots are for system A, that bubble column, and the orange X's are for system B. And in general, we're getting longer filter runtimes in the bubble column. And this has actually been something that we've been playing around with a pilot in the lab to figure out how do we need to operate these before we put it out into the field. And I think we've determined that the fixed bed needs to be backwashed every day. We're trying alternating a full backwash with a lighter one every other day. And then the bubble column needs to be backwashed every 2.5 days. So definitely operationally, there are some substantial differences between these two systems. And as I mentioned, with the intermittent operation, we've been able to test the resiliency of these systems. So when looking at this sort of regular intermittent operation of 9 hours per day and 5 days per week, these data are from 1 hour after startup, after it was offline over the weekend. So we have nitrate in the top row and nitrite in the bottom row. And with influent nitrate of a little over 15 milligrams per liter, we see after an hour of being online, the effluent concentrations were 0.35 or 1.4, with really small levels of nitrite in the effluent. And so within an hour, these systems are back online and they're responding quite quickly. And looking at the extended shutdown periods, we've observed complete denitrification, so the nitrate in the effluent is less than 0.5, and nitrite also less than 0.5. That was achieved within a day after startup, after it had been offline for a month. So this quick reacclimation is good news for small systems, at least for the heterotrophic denitrification. So to summarize the comparison between these two systems, in one we have a gravel bed and this nitrogen generator. The other is just a dual media packed bed. We have a slightly lower acetic acid feed in the bubble column, and sparging with nitrogen achieves a low DO at the top of the bed compared to the system B. Those systems are taking an influent nitrate of around 15 milligrams per liter and producing an effluent that's less than 1. There's definitely some scatter in here, but after tuning the system, we're getting low nitrate and can get it so that there's no nitrite accumulation. System A has slightly less biomass and lower biological activity in it, which is good from an operational standpoint. And in the bubble column, we're getting longer filter runs. To conclude, I hope I've shown that biological treatment is a viable nitrate removal strategy for small groundwater systems, and it could be more cost-effective than ion exchange or RO, particularly when you look at the costs associated with disposing of the brine. These reactors, heterotrophic denitrification, is resilient to changes in operation and can be operated intermittently and restart quickly. This innovative bubble column reactor could be beneficial for small systems because of longer filter run times and the lower acetic acid feed. And our ongoing optimization efforts include playing with the loading rates, looking at different media types in the contactor, and we're also very interested in testing this in the field and getting a pilot going out in the field and under a wider range of conditions and background chemistries. So if you're interested, please contact me or Darren, and I'd say we need to do some further assessment looking at the pros and cons or advantages and drawbacks of the different denitrification reactors. So that's some ongoing work. And with that, I will pass it back to Wendi. Thank you.
Great, thanks, Asher. We did get a lot of questions come in, so we look forward to answering those after all three of our presentations. And just a reminder to go ahead and submit any questions you have now through the webinar control panel. Our second speaker today is Dr. Chad Seidel, President of Corona Environmental Consulting. He's going to be presenting on consolidated management of nitrate treatment. Chad is also an adjunct faculty at the University of Colorado Boulder and has more than 20 years of experience serving water utilities, particularly focused on policy and small system issues. He's currently serving as co-principal investigator on the California-funded projects with UC Davis on consolidated management of nitrate treatment, implementation, demonstration, and affordability study, and the Assessing California's Vulnerable Drinking Water Systems for Risk and Solutions, the statewide needs assessment you might have heard about. Okay, well, with that, Chad, the virtual floor is now yours.
I'll unmute so you can all hear me. Did the share work? It looked like it started and then stopped. Now we're good. All right, so thank you so much, everybody, for joining. It's really a pleasure to get to connect with everybody virtually. Doesn't quite match the expectations of hanging out with everybody in Cincinnati like we've really appreciated over the years, but glad to be back and talk about what I would call the long and winding road with respect to this effort of assessing consolidated management of nitrate treatment. You can cue the music in the background if you want with that. But I'm going to give an update to a project that is ongoing in the state of California, has been for quite some time, which is just called, as we described, the consolidated management of nitrate treatment, really assessing implementation, demonstration, and affordability. This is a state-funded project. I'm going to give an update of the continued efforts since I've previously talked about this in a handful of different venues, talk about both the challenges that we've faced, which frankly have been one after the other, but progress that's being made as well. Certainly encourage folks to be watching the updates on the website that's listed there on the right. First and foremost, definitely have to acknowledge the team involved here. Dr. Jeannie Darby, who's the principal investigator at UC Davis, all of my colleagues at Corona who've been a key part of this throughout the years leading to this, our participating water utilities, Rio Bravo Greeley Unified School, Lindsay Strathmore, and Woodville, the state of California folks, both at Division of Drinking Water and the Department of Water Resources, all of whom are frankly just tremendous people committed to the cause of addressing the needs that small water systems face, in particular addressing nitrate, which has been a problem for a long time and likely to continue to be a problem until we overcome some of the challenges that we face. And so glad to have that focus. Also want to give a shout out to Eugene Long, who gives a talk tomorrow about implementing innovative treatments in the state of California. He's a key part of this project, and certainly encourage you to listen into his talk tomorrow, as he and others in California are working to just do exactly what this project is doing, innovate ways to solve problems that have been pervasive for a long time. So Asher did a great job in the previous talk talking about why nitrate's a problem. And this is kind of the same description of the fact that these dots represent where nitrate MCLs happened over the period of 2013 to 16. Those that have red dots have had violations for more than 3 of those years. You'll note that a lot of those are in California. California has been intentional about addressing this problem. And so as a tie-in to the talk that was given by Michelle Frederick earlier about California's SAFER program, which is really in response to their Human Right to Water initiative, you'll note that nitrate comprises a compound at 15% of the time of those Human Right to Water systems. It's a primary contributor, and it's often confounding other contaminant challenges that are faced. So we want to be proactive about addressing that, and nitrate treatment is one of the options that has to be looked at. We often go back to work that started this concept. This was published back in 2014 by Vivian Jensen when she was a PhD student at UC Davis, that pulled together work from an American Water Works funded effort and state of California funded effort on how do we address nitrate in potable water supplies these days. And often I point folks back to this resource, as many people refer to it as the Bible with respect to addressing nitrate, which is a nice compliment, but more so it's important to just, it puts a historical marker on how we as a community have addressed nitrate treatment in potable water supplies. It speaks some to the challenges that small systems face. Frankly, this project is an outcome of those realities, because if we think about nitrate treatment in a big sense, the first thing you want to do if you've got a nitrate problem, avoid nitrate treatment. Figure out how not to have to implement nitrate treatment, because it's a challenge, even more so for smaller systems. So consider other supplies, consider blending, consider ways you might just avoid the nitrate treatment in the first place. But if you have to get into the treatment approach, you then have to discern whether or not you want to go to the nitrate removal side, which is the focus of this particular project, or as Asher talked about, the nitrate reduction side, which has a number of inherent benefits, particularly with respect to destroying the nitrate and not having the same type of concentrated waste streams that can come from the nitrate removal side. But that said, while those technologies continue to be invested in and researched, there are dozens and dozens of small water systems in California and elsewhere that really do need a solution today, and we've got to overcome some of those barriers. And so in the nitrate removal side of things, we've got ion exchange as the predominantly used approach, especially in some areas where the discharge of a reverse osmosis waste brine just wouldn't be acceptable, or there's not enough water in the first place to support that. So this project is focusing on this train, but it then has to overcome the real challenge. So we can accept nitrate's a persistent non-compliance issue, especially for small systems, but it's expensive to treat it, even with established treatment technologies like ion exchange. And there's concerns with waste disposal. So our collaborative team over, many years, it's pushing a decade now, we've been trying to figure out how to better address these challenges, and could a managerial consolidation approach make nitrate treatment more feasible or cost effective? And so we were fortunate to be able to put forth a application to the state of California under their Proposition 50 funding efforts several years ago to address this. We received a $5 million grant to install and operate strong base ion exchange systems in selected small systems, and then operate them over a 3-year period. And that operations piece is a unique aspect of it. More often than not, these types of grant funds are not able to be used for operations. They're usually more so for capital facilities. This had flexibility to allow us to effectively research full-scale implementation and operation to answer some of these critical questions, not with an expectation that it is going to succeed perfectly. In fact, there's still some question if it will succeed at all, but we need the answer. We have to be able to have more information about how to move this ahead in addressing the nitrate treatment objectives and challenges. So we're simply testing this consolidated management approach and confirming if the costs, and here it says O&M, but really it's capital costs now too, how they can be lowered through some of the procurement approaches that need to be addressed for both the equipment and construction aspects. But then in operations, we've got management, operations, salt delivery, brine disposal, and even in that category, there's a lot of details, the collection, administration, and how you just go about purchasing services to address disposal. So we'll zoom in on where we're looking at these small systems. This happens to be the Central Valley of California, Lindsay, Strathmore, Woodville, and Rio Bravo being the 3 selected utilities. This happens to be in the heart of places where there's a lot of those red dots I showed on the map before, and what Asher described in some of his maps as well. Here's some simple pictures. And I always like sharing these for folks that don't have a good sense of what small systems really look like. This happens to be Rio Bravo Greeley School. They serve a population of just shy of 900 individuals, mostly students during the school year, but they also have some permanent residents in a handful of homes that are part of it as well. So there's 16 service connections. This groundwater well that's in the foreground pumps water to that tank, and they've got booster pumps to the rest of the system. Vast majority of it is for irrigation. So the fact that nitrate is above the MCL in this water doesn't necessarily mean that it all has to be addressed, but certainly enough for the potable purposes. Here we've got Tonyville, Lindsay Strathmore Irrigation District. Population serves about 500 and about 50 connections. They have a unique supply in that they can have both groundwater or surface water supplied through different sources. And for a system this size to have that complexity it's a challenge. But you'll note it's rural, very agricultural, and not many additional resources to be able to draw upon for other sources of supply. Woodville looks a little bit more like a typical groundwater system where you've got, a bit more recent infrastructure. This happens to be a more recently installed well, but like many other wells in this geography, has higher concentrations of not only nitrate, but other co-occurring contaminants, and they just don't have as much of a wherewithal for the typical technical, managerial, and financial capacity you need to address these types of problems. So originally, and we had a great project concept. We had an equipment provider in Ionix SG that was bringing new technology through strong-base anion exchange to the marketplace. We had 4 different water utilities that all shared nitrate as the common thread of needing to address nitrate. And we put forth the application, got funded, and a lot of things changed. Ionix exited the US marketplace. RRR found a different approach to address how they would address their water quality, moving from a centralized system to a point of use system, which is still being played out now. And then more so, the remaining factors complicated things even more. So instead of having the equipment provider as a part of the project, we now need to procure the equipment from a marketplace that perhaps isn't as well developed as we'd like, go through the site design. Then you'll note that just about every one of the systems has some other confounding issue. Tonyville, for example, we knew had nitrate and perchlorate, but further investigation finds that we've got arsenic of concern for both the MCL and even more so for waste residuals. Woodville and Rio Bravo Greeley School both have trichloropropane, which is not addressed by strong-base anion exchange. Requires some additional site improvements. The school has questions as to whether or not you go forward with full or partial flow, whether strong-base anion exchange is the best or reverse osmosis is the best. I'll just tell you that either side of that coin brings additional challenges and complexities in terms of corrosion control in a school, which is the last place we would want to have problems with respect to corrosion control for both lead and copper. So to give a little bit more insight, I'm going to share a little bit from what's a part of some of the other SAFER program efforts that we've been supporting. And in that effort, we were able to investigate 61 of the 311 systems that are out of compliance in California that are in Kern County. Went and did a detailed examination of those systems using PDF copies of sanitary surveys over history, and it helps give a little bit better perspective of what these types of systems face in terms of their challenges and why a consolidated management approach is likely imperative to be able to move forward. The first is size. So of those systems that are out of compliance that are in Kern County, so 61, 15 serve more than 200 connections. The rest, 75% of them, serve fewer than 200 connections. So this is where we have to focus our efforts. And we knew small systems were a big part of the problem, but they're not just small, they're really small. And that's key reality of the SAFER program as Michelle described previously on her talk earlier this morning. The next is just reliability of water supply and how the number of sources these systems have allows for you to be flexible with respect to water supply and or treatment or blending. And the striking reality is that almost half of these systems have only one source of supply. Doesn't meet the current California waterworks standards, but that is what they have, and that's what they have to be able to deal with. So when you're thinking about how to backstop water supply when implementing treatment and having concerns for failure, reliability is a pretty big concern. Next is, well, what's the age of that source of supply? And here you'll see most of them are pretty old. More than half are well supplies where they were constructed in the 80s or earlier. And so that starts to beg the question, if we're going to invest in a treatment approach for a given source of supply, should we do that on this source of supply? Or do we first then need to install the new well, hopefully with better construction and perhaps with a way to mitigate some of those contaminant concerns, but still recognizing, I describe it as a game of roulette. There's a good chance you're still going to find some degree of the same types of contaminants in most of these aquifers where you've got shallow water concerns, mostly nitrate, deeper water concerns with arsenic or uranium, and then other things like trichloropropane sprinkled in the Central Valley. So then we get to more practical things. How many of these systems have storage, water storage, treated water storage, or backup power? And a lot of them don't have storage or don't have enough storage. The majority don't have any or enough storage. And then most don't have backup power supply. And so again, when you think about treatment, you got to have pretty reliable supply for any degree of water treatment that brings with it a degree of sophistication that goes beyond turning a water pump and a chlorine disinfection pump on. And these are really significant costs and then operational challenges to overcome. One little footnote to the storage challenge. So when you don't have storage, you get this kind of graph for well flow rate. This happens to be a 24-hour period in Woodville where the well turned on and off about 80 times in that day. And it's just simply because the well supply is oversized for the typical potable production, but sized appropriately for requirements for fire flow. And if you don't have storage to meet that expectation, your treatment system is going to get hammered with on and off starts. And it's an issue that has to be addressed. It's not like it's a difficult thing to engineer, but it takes footprint, takes dollars, it takes operations, and then maintenance. A couple last things about the way that we look at these things is just the technical, managerial, financial aspects of things. Meters and then operators give us a sense of that. And generally speaking, most of those systems don't have meters yet. And they don't have the same degree of really contracted operations. So they're relying heavily on their own internal staff to address this, which is why we think the consolidated model will help. Last is the contaminant problem. In this particular region, nitrate is rarely by itself. More often than not, it's with other contaminants, TCP being the key issue, but this is different in all places across the country. Oftentimes nitrate has something else of challenge with it. Sometimes it's iron and manganese, sometimes it's arsenic, sometimes it's uranium, other organic compounds. And it just makes it so standard approaches like ion exchange and reverse osmosis, you got to deal with the waste residuals. As Asher talked about before with biological treatment, that's one of the benefits of biological treatment if you operate it as designed and intended. So we're working on overcoming some of the challenges that have become a reality of this project. And so when we shifted from the model of the equipment supplier being a part of the contracted research team, we then had to go forth with having the water utilities procure the equipment and the contractor. So it would be ideal to give the water utilities the funding up front, so then they can go forward and do that. But because of the funding mechanisms between the state and the utilities, we had to work through a reimbursement process that would allow us the ability to direct them, guide them, effectively just shepherd the process through the whole thing. So we've got a bit of a complicated funding process where UC Davis has the funds from the state and then they fund the utilities. And here's the description. So the money started with California Department of Water Resources. DDW is kind of a stakeholder overseer. Those monies went to UC Davis. UC Davis then funded our technical team who's directing these aspects of things, and they are just now in the process of putting in place the funding agreements to each of those three water utilities to then have them in the position to contract the equipment suppliers first. The equipment suppliers are going to be part of finalizing the detailed design around those systems as they're implemented. Then they will implement and will go forward and bid the contractors. And then they'll bid the contract operators and they'll bid the waste disposal. So this is much more expanded in terms of the numbers of contracts that have to be issued than what we intended to begin with. But one of the benefits of this is that if we can prove this model to be successful in the state, we expect it to be the stepping stone to reproducing it over and over again into the future for so many more of the small systems challenges in California, not just for nitrate. We're talking about all of the small systems, perhaps with trichloropropane, that will need pressure vessels installed for GAC and then operational contracts for GAC replacement, or take, for example, some of the other challenges that they face just for standard operations. So there's a lot of options out there to consider. So knowing that we then had to go to the market to get nitrate treatment equipment without having the equipment supplier as a part of the initial technical team, we face the simple reality that the current marketplace just has limited options for smaller nitrate treatment equipment. And when I say smaller, I mean treatment systems that are intended to produce less than a design flow rate of 500 GPM. Even more so, less than 100 GPM. And I understand why that market is not particularly well supported right now. It's basically because there's not a demand. And without a demand for those types of treatment systems, with the corresponding funding to support the demand to actually buy for the supply, you have this second bullet point of a history of lots of new providers to that marketplace, but those things just aren't sustained. And so we're working diligently to open up that marketplace, substantiate it with a meaningful approach where equipment providers and contractors and operators can bring their services to this market that ultimately has to be supported and sustained both monetarily and then obviously technically to make it work. So we're trying to be standardized, not proprietary, to achieve these objectives. So I'm glad that we're not in front of, I'm not in front of a big audience room where the people in the back of the row don't get to see all the details on this slide, but presuming most of us are just sitting in front of our computer screens like we have been for months and months, you can appreciate a little bit of the nuance of this process and instrumentation diagram for the ion exchange module. And I show this in its detail to get to the point that when you're talking about small systems, treatment systems, ion exchange is ultimately pretty simple. You just have ion exchange vessels, you put treated water through it until it's exhausted and you've achieved breakthrough conditions, and then you run regenerating brine back through it. The only thing that changes between a big system, say one that produces 2,000 gallons a minute versus one that supplies 60 gallons a minute, is really the size of the ion exchange vessels or the numbers of ion exchange vessels. All the other components, although they might be able to be downsized a bit, are still required, which means that there's a floor to which you can expect the cost for an ion exchange treatment system to start at. Because these things down here, you've got the nitrate analyzers, and you really need one that can analyze the raw water and the treated water, some cases for operational needs, but even more so for regulatory compliance purposes. And those things are not cheap. So shout out to people that are working on improved, lower cost, reliable, operable nitrate online analyzers. As soon as we can get those things proved, we got lots of places to put them in place. Now, shifting gears to the regeneration side of things, you've got the complexity of a regeneration module. And it has all the standard components of a typical ion exchange regeneration module. We've got a few more things that built into this to help us with the consolidated management approach and perhaps to optimize these systems to produce lower volumes of waste brine. But I'll just say the regeneration module has a expected cost. You can't make it smaller, and in many ways you can't make it simpler without having a higher cost consequence for the longer term operation. So with that in mind, putting together the specifications for bidding this, we intended to encourage standardized equipment, stay away from proprietary elements. We want to open the marketplace up for future things. We don't want to preclude different equipment providers from playing a role in this marketplace. We have a staged approach that includes design services, the equipment supply, commissioning, and acceptance and handover. Really important for the consolidated management model. And we had each of the 3 participating utilities issue site-specific bid documents. it was a lot more paperwork than we intended with the project to begin with, but we've made it through that process. Thankfully, we received competitive bids, and they very much demonstrate the threshold cost for those small treatment systems. Now, I'll tell you, we were in conversations with half a dozen or more potential equipment providers. We got responses from 2, and those 2 providers were fairly competitive, and I'll say that they were pretty darn close to what we had expected for the equipment supply bid costs. Those are what are shown here. These stacked bar charts are comprised of, going from bottom to top, stage 1 design services, sales equipment supply, sales tax, commissioning, delivery, and then acceptance and handover. And you'll note the predominant portion of the cost is the actual equipment. But note, as you go from the 60 GPM cost on the left to the 480 GPM cost on the right, they're damn near the same. And there's not really a way to make it cheaper for 60 GPM. So getting to some of the questions about consolidation begs the question, man, if you've got a cluster of small systems that need one nitrate treatment system, if it were bigger, maybe some consolidation, physical consolidation could also help here. Keep in mind that these costs go up exponentially per unit volume treated as you get to smaller and smaller systems. And we're trying to overcome those boundaries. So next steps are where we're at. So we're grateful that UC Davis has sent the funding agreements to the utilities, so they have now a vehicle to receive dollars and then spend dollars under the direction of the overall program. The local design engineer, QK, has completed the site designs, and the equipment, or the utilities, are going to move forward in signing the contracts with the equipment provider. Next to come is the general contractor bid packages. There's going to be another big question mark when we get to that. You know, what is the marketplace for having local contractors bid these projects? They're pretty straightforward, and there's a pretty good marketplace to support the needs of small systems when it comes to this type of infrastructure. But anytime you're funding things through a state program like this, it opens up some doors for some questions and concerns where you might have some limited response, and we're trying to address that as best we can. We're pressing as hard as we can to have this project construction started in early 2021 and start up still in 2021 and run these things for 3 years. When I've given talks about this project over the last couple of years, it just seems like we keep kicking the can down the road every time we say it. However, in every one of those instances, we're making really good, meaningful progress in overcoming the challenges, which have been the same challenges precluding these systems from solving the problem in the first place. And so we're eager to keep sharing the results of this, developing approaches, whether it be contractual or technical or operational, to get past these issues. These systems that have been struggling with these challenges, they deserve these answers. Their communities deserve clean, safe, reliable water. So a couple of key reminders and lessons, and I've used this slide before, but always important to recognize, smaller doesn't mean simpler. In fact, it often means more complicated and less informed. You're going to have data gaps you got to overcome to address what the real problem is. And every system is unique, so you can't assume that one standard solution is going to work in all places. You got to do the due diligence up front to consider what those challenges are, to make sure you're not going to create a bigger problem after the fact. You know, you don't want to just take the simplistic, hey, use reverse osmosis and discharge the waste brine locally for the school. In the end, in that example, the cost and operational complexity of the corrosion control system for just using that approach was more costly and complicated than the nitrate treatment system in the first place. And so you've got to get into those details. And then you got to balance the sophistication of the system and the operational requirements, because there's still some capacity that has to be developed to improve upon operational capacity. And I want to keep encouraging everybody that's part of this conversation. Keep incentivizing improvements and innovation with nitrate treatment, whether it be biological treatment, like Asher talked about, new sensors, new approaches to addressing some of the challenges of start-stop conditions. There's a lot of need for it. And I think the way that the state of California is investing in this is the way it's going to have to happen. Those small systems can't pull their bootstraps up by themselves. They need help from others in a more cohesive, collaborative way. So we're going to move forward. We still think the capital is critical to the affordability. I didn't even get into the details about how we think the consolidated management is expected to provide lower O&M costs, but the capital cost alone, by procuring it together, is saving dollars. And we know that we've got to address the affordability issue, and this project is going to keep informing it. This with context like what Asher's doing, like what the POE/POU presentation was about this morning. That's what I love so much about this conference, is that there's a common thread and theme of everybody chipping in to do what we can to solve these problems. So stay posted on this subject at the project website. Happy to answer questions. I'll be running through those as we move to the next speaker. And thanks again for being a part of this virtual version. I'll look forward to seeing people when we get to meet back together next time too.
Great, thanks, Chad. Some nice takeaways there at the end. I really appreciate you summarizing that for us. So our third speaker today is Stefan Buck. He's the general manager of NSF International's Global Filtration Division. He's going to be speaking with us on industry trends affecting drinking water treatment unit standards. And in his role as GM, Stefan is responsible for NSF International's certification services for point of use and point of entry drinking water treatment systems and components. He joined NSF in 2013, and he's been the business unit manager for NSF's Global Water Program Filtration Division since 2014. So with that, Stefan, I'm passing the presentation over to you, and you can go ahead and take it away.
Excellent. Thank you very much. And good afternoon to everyone. I appreciate you taking the time to join us today. So before I get into the contents of the presentation today, I just wanted to give a little quick overview of NSF International to those that may not be familiar with our organization. So NSF International is an independent, not-for-profit public health and safety organization. Our sole mission is to protect and improve human health through a number of pathways in a number of industries that we operate in, one of those being drinking water. Our organization's focus, essentially, in order to complete that mission, is to do that through developing standards, testing products to those standards, certifying products to those standards, conducting audits of the manufacturing of products, and also in food industry, providing advisory opportunities, and also training options. The foundation themselves, the organization was founded in 1944 in conjunction with the University of Michigan School of Public Health, and back then was founded as the National Sanitation Foundation. However, today the organization has grown quite a lot larger. We now have our headquarters in Ann Arbor, Michigan. We have over 58 offices and lab locations around the world, and therefore can no longer just be national, and so now identified as NSF International. To date, we have developed over 80 consensus standards and 85 different protocols, and have strong ties with lots of regulatory associations both in the United States and globally, and are one of the few, one of the World Health Organization collaborating centers. So we do work with the WHO on a number of opportunities as well. So that being said, I wanted to get into some of the current trends that are affecting the drinking water standards for point of use and point of entry products. There are a number of things that are currently ongoing, and this is a general overview of some of the things we'll be getting into. But one thing that I'm going to discuss a lot are the discussions of, or I'm going to start talking about task groups and a joint committee. And so I wanted to kind of provide a little bit of background on what that is. NSF International is the secretariat for all the NSF ANSI drinking water treatment unit standards. Therefore, we house the maintenance of those standards. And in doing so, it is all conducted through a consensus process in which we have a joint committee of approximately 30 people that help to maintain and vote on changes to those standards. That group of 30 people is divided equally into three groups: one of regulatory agencies, one of manufacturers or industry folks, and then just users. And NSF International represents one of those voting seats on that committee. And we have members with EPA, Health Canada, Other certification agencies are also on that committee. And so this committee meets annually and work throughout the year to ensure that the standards are maintained and kept up to date with some of the changes in technology and also in the industry in order to provide the public health and safety of consumers of these products. So the first topic I wanted to get into was lead reduction in the drinking water treatment unit standards. There has recently been a change in the standard, which was published in the 2019 version of both NSF ANSI 53 and NSF ANSI 58. 53 covers products that typically contain activated media, filtration types of products, whereas 58 is the standard associated with reverse osmosis. So what occurred was that there had been proposed changes and adopted changes now of a drinking water lead criteria of 5 parts per billion. The previous version of the NSF ANSI standards had a pass-fail criteria for products to meet a reduction of lead in the drinking water at 10 parts per billion. The influent concentration of these tests is 150 parts per billion, and they're tested at 2 different pH levels, one at 6.5 and one at 8.5. And so upon understanding that there was proposed changes and some agencies had already adopted a new limit of 5 parts per billion, there was proposal to the Joint Committee in order to revise the pass-fail criteria for the NSF ANSI standards and match that at 5 parts per billion. This passed and has now been included in both standards and has been published and is effective immediately. So products moving forward when certifying or when trying to obtain this NSF certification for a lead reduction claim now will have to meet this new criteria of 5 parts per billion. Part of the change also assessed the current status of products that are certified, because there are a number of products already in the marketplace. And in that investigation, it was identified that the majority of those products would likely meet the same criteria, the new criteria. So hence there was a need to put this into the marketplace effective immediately, so that we are certifying and testing products to the most recent version of the standard. So on top of that, there's a number of other items being discussed surrounding lead within the Joint Committee and within the ANSI standards. Ever since the situation in Flint, in which we had issues with lead in drinking water, there's been discussions as how to address the test methodology within the standard. Is it conservative enough for the standard itself? And so a task group was formed in order to assess and investigate the possibility of developing a performance claim with an influent challenge of higher than 150 parts per billion. Now this comes with a number of challenges within it in trying to develop a test method that can be reproducible across multiple labs. But as it's been ongoing and as discussions have been had, one thing that was most recently that had come up, which is now taken sort of a priority within the task group, is the investigation of the impact of orthophosphate in the challenge water. So currently the test method within the standards don't include any orthophosphate. And orthophosphate, as probably many of you are familiar with, is a commonly used corrosion inhibitor that is used by not all, but a fair number of municipal treatment systems. And so the task group now is trying to identify a new test method that they could propose to the Joint Committee to potentially include within the standards that would develop a new test at a pH of 7.5 that would also include orthophosphate, as the inclusion of orthophosphate may have some sort of impact on the particulate size of the lead within the testing. So currently, this validation and this investigation is ongoing with a variety of labs, including all the other certifying agencies. And we are going to be looking to see some updates from that within a year or so from the task group. So another industry trend that's under development with the standards is an inclusion of manganese reduction as a performance claim. Now, manganese reduction is already within the NSF ANSI drinking water treatment standards. However, it's included under standard 42. And 42 is very similar to our standard 53, with the only major difference being that the performance claims under that are considered aesthetic performance claims, and therefore don't have direct impact to the health of a consumer. Now, in 2016, Health Canada had issued a new MAC for manganese of 100 parts per billion. Having issued that, they notified the Joint Committee of this new maximum acceptable criteria, which now essentially makes manganese a health-associated claim. During the time between 2016 and today, the WQA, the Water Quality Association, did publish ORD 1901, which is not an NSF, which is not an ANSI standard, but they published it as a temporary standard until those health-based claims within it could be added to the relevant NSF standards. And so it was presented to the Joint Committee in order to basically adopt that WQA ORD 1901 and essentially move the manganese reduction claim from standard 42, apply it to standard 53 as a health reduction claim, and in addition, apply it to the other pertinent standards such as 58 for reverse osmosis systems, and also standard 44 for water softeners, as they have the ability to also reduce manganese from the drinking water. It should be noted, though, that under standard 42, the current pass-fail criteria is 50 parts per billion. So if there are products that have that certification, they would technically meet the MAC under Health Canada. But again, this task group is ongoing, and we're looking to hopefully get some updates on this by the next Joint Committee date. The next update within the industry is the new low lead criteria associated with fixtures and also point of use devices. So this isn't necessarily an update to the drinking water treatment unit standards, more so as it's an update to manufacturers of point of use and point of entry products. So the EPA just recently published the new or the final regulation on the use of lead-free pipes, fittings, fixtures, solder, and flux for drinking water. And within the new regulation, they will now essentially require that the majority of point of use and point of entry products meet the definition of lead-free in accordance to a standard such as NSF ANSI 372. And NSF 372 is the low lead standard, not to be confused with a lead reduction claim under standard 53, but it applies to all product types in contact with drinking water. One thing to note is that within this regulation, there's an exclusion for carbon-based products in which the surface area of the carbon is not to be included within the lead content calculation of the product, just because the surface area of our carbon would be immense. And the other thing to note is that there is a 3-year compliance period now. So over the course of the next 3 years, we're expecting to inform all manufacturers' clients that there is this compliance requirement within the United States in order to get products to meet this definition of lead-free. There are some other exceptions within the regulation, but these are the primary ones that would be impacting the point of use and point of entry drinking water treatment unit world. One thing also to note is that for products that are certified just to standard 61, which is not necessarily point of use products, it's for more point of entry and also faucets and everything else, there is a low lead requirement within it already. So products moving forward certified to standard 61 will meet this definition moving forward. Another new trend that is re-emerging is microplastics. And so a few years ago, there was a number of media articles that flew across the globe regarding microplastics and their potential impact within drinking water and also within bottled water. And one thing to know about the drinking water treatment unit standards and the point of use industry is that it's very consumer focused. And so, a lot of things are driven by what consumers are looking for when they're looking at their drinking water. And so this was a big topic that was hitting the media airwaves. And so it was proposed at the time in order for the Joint Committee to kind of investigate the possibility of adding reduction claim for microplastics. But at the time, there was just a lot of unknowns about it. The task group was developed. Not a lot of traction was made until recently, until it's kind of repopulated per se. And so one of the charges of this task group is to develop a scope or a definition, I should say, of what a microplastic is in order to then determine if there is a possibility for performance tests within the standard to address microplastics, or is there a possibility to use a surrogate test within the standards already to address this? And so the task group is really just getting started at this point in time and investigating definitions for microplastics from other regulatory agencies. I know California has one now. So we'll be looking at a lot of those in order to get the group moving forward, investigating this option, and then potentially having a claim for the reduction of microplastics in the near future. Okay, PFAS. So this is definitely a hot topic in the point of use world, as it's being identified nationally across many states, and as we are understanding more and more about PFAS and the number of different compounds within the PFAS family that are being identified. So currently in the NSF ANSI standards world, there are certified products that can claim the reduction of both PFOS and PFOA. These claims have been available since 2016, in which products were certified under NSF P473, P standing for a protocol. The protocol was then moved to the Joint Committee and then adopted under the applicable standards of NSF ANSI 53 and 58. So one thing to note is that there will be references, or you may see references to both P473 and standard 53 for the same reduction claim. There's an adoption period in terms of changing references for both manufacturers and regulatory agencies and anyone that has any publications on these two different protocols and standards in order to update them. And so by June of next year, we're expecting all references to P473 be removed from anywhere, so that there's less confusion in the marketplace moving forward as to what to look for within a product that has that PFOS and PFOA reduction claim. The current status of the standard requires a pass-fail criteria, which is equivalent to the EPA health advisory level, which is 70 parts per trillion combined for both PFOS and PFOA. And since this publication, there have been a number of states that have gone on and adopted or established their own criteria for PFOS, PFOA, and also in addition to other compounds. So one of the challenges for the Joint Committee and for the standards body to identify is, what compounds do we investigate to add to the standard, at what levels? A lot of the new criteria coming out have very, very low levels of pass-fail criteria, somewhere 10 parts per billion or per trillion, some may be less. And so the task group was developed in order to identify the next round of essentially PFAS compounds that could be added to the standard, and then identify how that could be tested, how that could be reproduced in different labs, so that the testing can be done across a variety of laboratories. And so the current status of this task group at this point in time is looking at the following PFAS compounds. And so validation and testing is currently under progress with multiple labs in order to assess the analytical criteria associated with these compounds, assess the feasibility and cost effectiveness of the test method for these compounds. And so being such a high priority within the regulatory world, this is taking precedent within the Joint Committee And so I would expect us to see some significant action done on these particular compounds being added to the standard within probably 6 to 12 months, if not sooner. And that would therefore allow for more products to be certified, show compliance to these to the standard for PFAS reduction, and also allow additional supplemental assistance for consumers in order to help reduce these compounds from their water if they're being affected by it. Another one I wanted to bring up is 1,2,3-trichloropropane. So this is an issue that was brought up this year to the Joint Committee. 1,2,3-TCP, as it's often referred to, is chlorinated hydrocarbon that has high chemical stability, man-made chemical that's found at industrial and hazardous waste sites. Currently, there's no federal MCL for this particular contaminant. We do know that it's of importance in California, and I do believe California has put in place either an advisory level or an MCL. New Jersey also has one as well, very different. And so with the importance that this is getting in some of the states, there was a proposal to investigate the potential to add this compound to the standards as a performance claim for a reduction claim. And so this one is also under task group and is also undergoing validation with some of the labs. And I would anticipate that based on the progress that it's making, we probably will see this within the next publication of the standard. And the idea then would be to just wait to see how many products would then start testing and get certified for this one. But this one has made a lot of progress and a lot of traction this year. And so we should see some changes to both to NSF and C53 on this one within the year. That is the last one. So I do thank you for your time. I haven't had a chance to see if there's any questions, but I will take a look and do my best to help answer them. Thank you.
Thanks, Stefan. Yes, we did get a few questions in. I'm sure there will be a few more that come in. Feel free to keep sending those in. And we are now going to transition over to the question and answer portion of this session. So we've got over half an hour here to get through these questions. So Asher, I think I'll start with you since you were our first presenter, and we got several questions in there. There were a few questions about the setup for your work, and so maybe we'll start with those. You know, what type of gravel bed was used? And then there was another question about an aerobic bioreactor after an aeration process, and if you could explain what contaminants are removed during that process.
Yeah, so the gravel, I think I found the question if maybe it was crushed limestone. It's not. I guess I'm not quite sure what the composition is. Just sort of the gravel that I played in a playground. And the aerobic biofilter, that purpose, in part it's to remove flocks. So if biomass gets shed from the anoxic bioreactor, then those can be removed in the filter, and then you hit your turbidity standard. Or the other thing is it can clean up any organic, or not any, but it can help to remove DOC that might come out of the anoxic bioreactor. So if you overfeed your acetic acid, then it would get consumed there. And for some of the soluble microbial products that might be biodegradable, then those concentrations could be decreased. So it's sort of a polishing for particles and organic carbon.
Okay, great. And then another question for you, Asher, is there any way for this kind of biological treatment to be feasible for systems that do not use chlorine, chloramine, or other injected disinfectants?
Yeah, I think that would just depend on the disinfection requirements for wherever you're located. I think some studies have looked at pathogens in biological treatment systems, and for the most part, like pathogens aren't going to be the dominant microorganisms in these biofilms. So it just depends on what your disinfection requirements are. But you will have higher HPCs or higher ATP coming out of a biological treatment process than probably something that's just physical chemical.
Okay, and Chad, we've got a few questions here for you. Lots of questions around brine disposal. I think there was one question that kind of summed up everybody's, which, you know, kind of what do you do with the brine disposal, and is there a market that you know of where the brine could be used for some beneficial use, maybe agriculture, or is this always a cost to the utility?
Yeah, it's a great question. It's certainly a key area of the intended research and implementation. The standard approach used for strong base anion exchange today in the Central Valley of California, which has pretty stringent limits on wastewater receiving to local wastewater systems in terms of salt, total dissolved solids, and conductivity, really precludes any of those strong base anion exchange treatment system residuals that are a strong salt solution from being disposed locally. So one of the high cost aspects of operating a strong base anion exchange system in the Central Valley, and frankly a lot of places in California in particular, is the trucking, the hauling of that waste brine to acceptable discharge locations. Some of those are commercial waste receiving facilities. Some of them are actually municipal waste receiving facilities, but they more so have coastal wastewater outfalls that are accepting of the higher strength salt solutions. And clearly a wastewater system can accept the higher nitrate load. It's just part of the wastewater process. That's one of the cruxes of the consolidated management approach, because small systems, like of the size that I described, only produce a small amount, relatively speaking, of waste brine. It's not like they're going to produce enough brine to really warrant independent trucks coming to pick up the waste brine and take, say, a 3,000 gallon tanker truckload to a waste receiving facility that's farther away. That might be, you know, as much as 15 cents a gallon to dispose of it, plus the transportation cost on top of it might be 50 plus cents a gallon for disposal, which is pretty ungodly for a small system. So consolidated management is discerning whether or not we can have one truck go pick up from 3 places and take it back. That alone saves a lot of the extra cost. So we're looking at that. There are other approaches that are being looked at to consider how you might change the regeneration process. There's some thoughts to use a potassium chloride based approach and then recover struvite for fertilizer production. There's some other treatment technologies that actually produce they're lower strength solutions that could perhaps be used for fertilizer, kind of the complete circle of nitrate, if you would. And then the other question about the reverse osmosis waste brine, again, for the same reasons that there are strict limits on how much salt can be discharged in certain places. By and large, the use of a reject water from an RO system is precluded from being used for ag purposes. There are some unique circumstances in California where that's being applied in other places, but it wouldn't have worked in these small system cases. So a lot of, you really put the pin on the key issue of the problem, the waste residuals. It really drives it all.
Yeah, and another great follow-up question here for you, Chad. It says, I see the biggest challenge for small water systems implementing biological treatment systems is the qualified operators. And obviously this is more complex treatment, and you know, so not many operators from small water systems can necessarily handle that. So do you have thoughts on how we overcome that challenge and kind of what the needs are out there?
Yeah, absolutely. There's a huge need for growing the capacity of the existing operation staff that are serving the water community, not just in California. I mean, this is across the country. We see this all over the place. And then bringing more people into that community to be water operators. We expect that the consolidated management approach that we're researching will be able to better prove out how we can leverage consolidated management with sharing operational resources. So when nitrate treatment systems using biological treatment are ready for small systems, we'll have that same degree of additional operator certification capacity to help those. You know, it's any one of these systems can't afford one operator on their own. And one operator doesn't need to spend all their time at one of these systems all alone. So as you get economies of scale of addressing multiples of these, it becomes more feasible for that. So we got to consolidate, even if it's virtual, consolidation of operations, as well as bring more people into the field. So encourage your friends and families to get into the business of water operations.
Yeah, that's a good pitch. Job security for sure, right? Well, there's definitely a lot of other small system questions in here, but I do want to bring Stefan into the conversation. So we've got a question for you here about how quickly new or existing products will be certified to these new lower standards. Basically, how long is this phase-in process? And then specific to the lead content and the reduction in the lead content, is there a plan to help identify the markings on a product that meet these new lower standards?
Yeah, thank you, Wendy. That's a great question. So each certifying agency will have probably their own approach when addressing the identification of these products. From NSF International's perspective, when looking through our product list, we identify that pretty much all of them already met the new criteria. And so we didn't impose any type of implementation period, which sometimes may happen to allow manufacturers of products to meet a new criteria. And based on the importance of the lead reduction claim as well within the industry, we thought it in best interest to make sure they essentially the new criteria is put into effect immediately. So any product coming to NSF for testing as of the publication of the standard now has to meet that criteria. So for us, there's no distinction in the markings. All products just have to meet the new criteria of 5 parts per billion of reduction of lead from the drinking water.
Okay, great, thank you. And maybe we'll circle back up to Asher again. There's a few more questions about some of the information you presented. So I think you mentioned that acetic acid is a preferred option. Maybe you could explain why that is, and then we can get to a few other questions.
Yeah, so I think there was also a question of like our ethanol or methanol NSF certified for drinking water in the US. And so Stefan, I'd have to ask you about that one, but I think acetic acid is, and I don't think methanol is. I don't know if you want to chime in.
I'm by no means an expert in NSF ANSI Standard 60. My recommendation would be to check out the website for the certifying bodies. And so you can go to nsf.org for NSF certified products and search by standard and by chemical type. So under that standard, you would be able to identify pretty quickly whether or not there were certified products in the marketplace.
Okay, thank you. I think I've heard that adding ethanol to drinking water is, there are some concerns about public perception around that within the US, but ethanol definitely is used in Europe at some of the full-scale systems that I've seen published about. Basically, you want a simple organic carbon source.
Okay, great. And then we had a few questions about flow. Asher, I think under your presentation, what the minimum GPM of flow that you should have for your system, and then what the flow capacities are for some of these removal strategies.
Yeah, so flow would be, I don't know, it sort of depends on like the diameter of your vessels and how many vessels you have, and then what the loading rates are, and what sort of empty-bed contact times the bacteria need for this. I think denitrification is a pretty fast reaction, and you can have, I think we can get, we were running with empty-bed contact times of 14 minutes, but I think we can drive that lower. So for the flow, I think it's more a design question than like the fact that it's biological.
Okay, yeah. And then A question here, I think this is an interesting direction. Would this be an effective or economical solution for private well contamination, and what other contaminants would be looked at for removal?
I mean, other inorganic oxyanions like chromate and perchlorate and bromate, they can be removed. Some VOCs also can be removed with anoxic biotreatment. I think there was a question on how, like, a bubble column, if you would want to use that when VOCs are present in the water as well. And that might be a situation where sparging with nitrogen might not be the preferred design configuration. So those are some of the other contaminants that could be removed as long as you get your timing and the substrate feeds where they need to be. In terms of a private well, I don't know if that's thinking about like an individual homeowner. I don't think I would recommend this as any sort of point of entry treatment system. I don't know if that answers the question.
Yeah, if that didn't answer your question, I don't see who sent that in, but feel free to send up a follow-up question. I think we'll have some time to get back to it. Okay, so Chad, a few more questions for you here. Have you looked at off-the-shelf POE devices and being able to scale them up for the very small systems that you're working with?
Yeah, absolutely. In fact, for the school example, the expected reverse osmosis treatment system was effectively a POE sized system. It was not particularly large. That system, the RO system, was actually quite a bit smaller and fairly simple. And then you have a treat a portion and bypass the other portion to get your expected treated water quality to go to the potable water supply, with the remainder of everything else being used for irrigation. So we downsize it significantly. The waste residual from that system was going to go to septic, which surprisingly was even going to be able to be capable because of the size of the school system that most often wouldn't be acceptable in other smaller systems. So in the RO sense, yes. In the point of entry space for strong base anion exchange, that's not a pretty routine market segment. There's lots of cation exchange softeners for point of entry or point of use, but those systems are dramatically simpler and don't have the operational controls and fail safes necessary to provide potable water under a condition where you can't accept nitrate exceedances. And so that's where there's this gap in the marketplace. Same in terms of the biological treatment. Some of the equipment providers wanted to go in the biological treatment direction, and by no means are we against that. In fact, we are wanting to encourage it, especially in a consolidated management model. But there's not yet enough consistency around the way those systems would be applied, especially in the 100 GPM and smaller flow range. I think 500 GPM and up, pretty good, robust expectations, pretty good marketplace for those pieces of equipment. Between 500 GPM down to 100 GPM for a given treatment system design flow, that's where there's a lot of, kind of no man's land. And then below 100 is like, you do start begging the question, man, our point of use device is better here. I will tell you that one of the communities that dropped out of the program that went to point of use using RO point of use for nitrate, community preferred it because it tasted better, because the RO did a better job of getting the TDS down. But like the point of entry, point of use device talk that was on the program earlier today, they're struggling with 100% acceptance. And even in a community that all sees the benefit of it. That's why if there were an easy answer to these problems, I'm convinced they would have been solved already. So you kind of got to expect every corner you come around, you're going to find some other aspect you got to overcome.
Yeah, some new challenge for sure. When we have a comment here that I think kind of gets a little deeper of isn't the equipment and service market, this disparity you talk about, this no man's land, isn't this a worldwide scenario? Aren't small countries and developing nations also having these issues? And kind of what factor does that play? And then a question here from the same asker: can consolidated regeneration happen at localized area sites?
Yeah, Actually, I'll answer the latter question first because it kind of leads into where else it goes. We have looked into ways to, instead of regenerating at the point of treatment, taking the vessels and regenerating them at a single regeneration facility. That's actually in place in a handful of places in California now for other purposes. The costs of that in this scale are higher. Because you got to move resin around so often. You know, if there were a longer period of time between starting a given fresh resin column and its regeneration period, it might be a bit more practical, but the duration of time between your generation cycles is just too short. You don't get enough bed volume to treatment. So, but that model is done, moving the resin instead of moving the waste brine. In terms of the global marketplace, that's a good question. You know, we try to keep tabs on the nitrate treatment marketplace all over the place. And there's people around the globe that are working to innovate new treatment solutions. You know, I've spent pretty much my entire 20+ year career looking at better ways to solve this nitrate problem, hoping one day we'll avoid having all these brine waste challenges. Biological treatment is the best we've done so far. To date, most, I won't say all, but pretty much almost all of the electrochemical or chemical reduction approaches have failed. There's still some light there that maybe we'll be able to make that work. But in terms of what would be expected for a small system to implement in the US, some of the expectations for equipment certifications, reliability expectations, and then general market availability of replacement parts and just simple stuff to keep the things operating means that the field of potential suppliers of the equipment and services gets narrowed down really quickly. And almost immediately you find yourself with, there's not enough people to supply these things to have a competitive marketplace for these needs. And I still just go back to the point that without, you know, there's a problem, there just hasn't been enough support to address the problem, which means there hasn't been enough money to substantiate and sustain a marketplace to fill the need. More and more states looking into pressing how to do this is going to keep driving that forward. Maybe then more international support will be able to come and be a part of it.
Mm-hmm. Yeah, and another kind of question in that same vein, how practical is biological treatment for nitrate for small systems where the operation of the biological removal system would be intermittent or only part of the day? Is that feasible?
I think we saw so far in our experiences that yes, these heterotrophic denitrification system can be operated intermittently and start producing water that's fit for distribution pretty quickly after being brought online.
I'll add past that from the operational perspective. I totally agree. I think it's totally doable, but is likely going to require some additional infrastructure around the treatment system, namely the pumping from the groundwater supply needing to match the supply of the treatment system, and then a buffer of treated water into the distribution system so you can just keep the system operating a bit more steady state. So I think in places where we've seen better success in those regards in real world small system implementation, having raw water storage and treated water storage can dramatically simplify that and add to the reliability of the systems. It also adds to the cost, but definitely warranted in many cases.
And here we have a question about kind of how small is small, and how small of a small system can it be feasible to use this? For example, will a bioreactor be economically feasible for a PWS that treats at 10 to 15 gallons per minute?
I'm gonna have to pass on that one.
I think it's tough to say that it would be. Not that it's not feasible. Absolutely feasible. If you want to be like a PhD postdoc researcher who operates that system for your small water system, definitely doable.
Where there's a will, there's a way.
However, it is not one that is a expect it to be set it and forget it kind of treatment. It requires a bit more diligence and hands-on involvement, and then just a higher degree of automation and instrumentation to make sure it's doing what you want it to do. So then that's why that threshold of minimum cost expectation becomes a problem. biological treatment has that same challenge like strong base anion exchange for instrumentation and monitoring.
Yeah, fair enough. Okay, Stefan, we've got a few questions here for you. Any trends in developing standards for endocrine disruption?
Yeah, so that's a good question. So we do have a standard out there, which is NSF ANSI 401, which is a standard that houses what we identify as emerging compounds and incidental contaminants. And so there are one or two endocrine disruptors that are already present within that standard as a claim for reduction, namely one of them being BPA. But that standard does house contaminants which are not known to be aesthetic issues or also not known to be health issues with respect to having a MCL associated with them. So I would encourage anyone to look at that standard at the moment to see what we have. There's 15 compounds that can be claimed under that standard at the moment, but it is an open standard as it will be able to add more compounds to them as needs arise. So keep an eye out on that one as it will continue to grow.
Okay, great. And then a question here asking what the difference is between some of the PFAS standards that you talked about between P473 versus NSF 53 and NSF 58.
Yeah, another good question, which is partly why we're trying to remove the references to P473 in the future. So essentially, it all came down to being a chronological timeline. When the need for PFAS reduction came out, the NSF developed a protocol first, which was P473. And the protocol was based off of test methods and knowledge from the standards already. And so that was issued first for products to get certification and show that their products could perform for the reduction of those two compounds. Once it got introduced to the Joint Committee, it was then adopted into the standards. So P473 doesn't exist anymore. Essentially now it's NSF standard 53, and you can get a product certified to that standard for the reduction of PFOS or PFOA. Or if you have a reverse osmosis system, those products are certified under standard 58. So the criteria is similar. The difference between P473 and what's in the standards now is the same, so there's no change there. Really, it all becomes what's your product type that you're certifying, and therefore it dictates what standard you go under. But the claims are the same. So moving forward, consumers and also regulators should start referencing just standard 53 or just standard 58 for the reduction of those compounds.
Okay, great. And we have a question here. I'm not sure which of the speakers it would be best to go to, but how will the acetic acid injection be determined and or calculated based on the different sizes of water utilities? Is that a Stefan question or Asher? Asher.
I got this. So the acetic acid feed is going to depend on your nitrate concentration and if there are other contaminants that you're trying to remove. And there are some theoretical ratios of how much acetic acid you would need per milligram per liter of nitrate that's present. But I'd say that's something to test out in piloting to really determine for that particular water.
Okay, and while we've got a few more questions for you, Asher, could you speak about nitrate sampling frequency of the treated water for assuming proper operation of the bioreactor?
Yeah, so we're currently putting together ASDWA manual of practice on biological treatment, and monitoring and sampling frequency is a big part of the chapter development. And one of those chapters will be dedicated to anoxic biological treatment systems. So I'm not sure from a regulatory perspective what that needs to be, but yeah, sorry, I can't offer a good answer on that at this point.
That's all right. We can move on to this next question, which asks how were the filters prepared for extended shutdown to prevent biofouling, and what was done after startup, and what parameters were used to determine return to service?
The beds were left submerged with water, and then for returning them to service, it just started flowing water through it again. After a couple hours, I backwashed. One time I backwashed with chlorinated tap water that had a free chlorine residual of 1 milligram per liter, and that seemed to help some with some biofouling. I don't know, I'd like, since we're feeding dechlorinated tap water here, the bacteria that seeded the filter are able to withstand some chlorine residual and be okay with that. So I don't know, I'm hesitant to suggest that as something to apply out in the field, but I think flushing water, running a few backwashes, doing some extended backwashes, and then monitoring the effluent water quality and seeing that the nitrate is low and that you're not accumulating nitrite, and those would be the indicators that it's fit to go back out.
Okay, and then can the backwash from both of these reactors that you talked about be discharged into the wastewater system?
I mean, as long as, like, here nitrate is the only contaminant, and then it's converted to nitrogen gas, so the residuals in that backwash water would pretty much just be biomass. So as long as the wastewater treatment plant is okay with you discharging those flows, and probably have some equalization basins so that you're not slamming it with a big flow rate all at once, then working that out, it should be okay. If you are removing other contaminants and then need some physical separation, or you're looking at some solid residuals of metals, then that would be a different sort of concern. But with just nitrate, I think checking out that the flows are okay, then that would be all right.
Okay, and Chad, we talked a little bit about this, but maybe if you have any additional comments, a couple of international related questions coming in. Which method of nitrate removal is suitable in developing countries, if you have an opinion on that? And then a comment that electrodialysis reversal treatment is one technology used elsewhere, example given is Israel, but no technology vendor in the United States is providing that product. And any thoughts on that?
Yeah, I'll start with the EDR approach. That is a technology that you'll read about in that critical reviews paper about nitrate treatment options for potable water supply. EDR is one of the technologies that is often listed as a best available technology. It comes with the benefit that it's kind of like reverse osmosis, but it can be even more selective at removing nitrate and less selective at removing the other salt-based compounds, typical cations and anions. And so it can have the benefit of providing a discharge water. It's not a brine so much as a concentrate is the more technical way to describe it. And in Israel, in fact, many of those treatment systems, they do use the waste concentrate, if you would, as fertilizer water for local agricultural fields. And actually, I was a part of an effort to attempt to demonstrate one of those technologies in California. We got about 2 years into the process, and unfortunately, one of the limits of the technology is that it doesn't have small-scale systems that are readily pilot testable. You can't really just build a tiny system like that. And so we had to move forward in implementing a full-scale system, and the international company supporting it changed their direction of where they were going with business development, and ultimately they didn't want to move that forward again. I guess then again, I think it speaks to the fact that there just hasn't been enough of a marketplace to support and substantiate outside technology providers to bring those types of solutions to the US. In terms of the developing communities in other places, strong base anion exchange kind of falls by the wayside really quick in underserved areas where you don't have reliable supply of the consumables necessary. You got to have a reliable salt supply. So that is most often thought to just not be usable. Any type of high pressure membrane process technically usually goes the same way. So more often than not, when nitrate is a problem in developing communities in more international settings, you try to do more to find a not contaminated water supply. do a better job of siting wells that aren't impacted by up gradient latrines. I've done work in Uganda that's specifically focused on that, and unfortunately there wasn't much attention to that in some of the areas, and there's a lot of high nitrate in some places. But when it comes to treatment, there still just aren't that many better approaches to deal with it without reliable consumables. Electricity, certainly chief among them. So there's just getting to standard disinfection is the primary objective in many of those cases. Going beyond that to then perhaps have some biological treatment that uses the available land area or water retention areas perhaps could be feasible, followed with disinfection at the end of it, but not one that is being as addressed there as it is elsewhere.
Okay, great. Yeah, some good thoughts there. And there's a question here. I'm not sure, Chad, you might know if this exists, if there's a life cycle cost analysis comparing ion exchange and biological nutrient removal, and maybe where that's available.
Actually, yeah, there's a couple of good ones. There are some that are actually even referenced in that critical reviews in environmental science and technology paper that was published in 2014. That, that's, gosh, 6 years old already. One of the projects that was referenced then was a Water Research Foundation study led by Glendale, Arizona, that looked specifically at strong base ion exchange and biological treatment at the time and used a number of life cycle cost estimates to get at those nuances. There have been follow-on activities, the part of other funded efforts in California that I'm aware of. Asher mentioned the ASDWA manual practice around biological treatment. I know a number of the co-authors supporting that effort have been a part of those things. So I would suggest, good old Google Scholar will get you to a lot of those pretty quick. If you put potable water nitrate treatment life cycle cost, they'll come up.
Okay, great. Yeah. Okay, and I think this is a question for Asher here in your in the denitrification treatment tests. Sorry, did the denitrification treatments test shallow water systems only or deep water systems as well?
I mean, at this point, we're using tap water and adding nitrate to it, so that's been my involvement. I think I was showing figures of nitrate contamination in shallow groundwater sources just to show some of where it is within the country. But I think in terms of the treatment technique, the depth of the well is like, it can be whatever it is. This is just, if you have nitrate in your water, this is one treatment approach that's viable.
Right, okay. And then have you monitored either bubble column or fixed bed immediately after startup? And if so, how long does it take to drop below the MCL?
That's a good question, and something that I want to look at closer. So far, I've looked at it like within an hour of starting back up after a weekend, or the day after being offline for a month, as I mentioned. But I think doing profiles like that is definitely data that we want to have.
Yeah, a TBD, or to be seen, perhaps. Okay, and I think we only have time for maybe one more question here, and this question is, for many groundwater systems, there's no storage and treated water goes straight into the distribution system. What's your opinion when using biological treatment? Should a treated water storage tank be included as a part of the project to allow long continuous operation? And are there maybe any inexpensive methods to monitor the treatment process continually due to the acute health risks of nitrate?
I think Chad has talked about both of these and the need for less expensive online analyzers. In terms of finished water storage, I think in my experience working with biological treatment systems, coming up with a backwash water source is always a critical part of the design. And you don't really want to be backwashing with chlorinated water, so using a clear well where you are maintaining a chlorine residual and getting that for a CT isn't ideal, so you could have this other storage tank with its cost and footprint. So I think in this system where you re-aerate, run through a filter, you're not at supercritical DOs, you might be able to pump right to distribution without, it depends on what CT you need. I don't know, Chad, if you want to add anything.
I think those are all great points. I've seen how some who have worked to implement these types of systems, both for research and application, have attempted to try to avoid hot water and treated water storage. More often than not, it seemed like those things confounded it. And so again, it just depends upon the scale you're dealing with. If you're talking about a 50 GPM system versus a 500 GPM system, you've got different buffers on either end. The smaller that range, I think the more likely it is to expect you've got both raw and treated water buffering supplies, just so you don't have to, volume buffer the volume, so you can keep the process more steady state.
Okay, well, that takes us to the top of the hour. I'm sorry we didn't get to all the questions. I think we had over like 700 participants, so we could have used a lot more time to get through everybody's questions. But I want to give a round of applause to our panelists. That was excellent. And thank everyone for joining us. We hope you enjoyed the session, and we hope you'll join us for the additional sessions at this year's virtual drinking water workshop.
Thanks all.
Thank you. Bye-bye.
Thank you.